All right. So these are the 2.1 notes on graphing polynomial functions. We're going to review some vocabulary that should be familiar with you. You might not know all of it. That's okay. And then have an opportunity to discuss something new called end behavior, which we're going to talk about a lot this year. So that'll be our first day talking about it. That conversation is going to continue throughout the year. So starting off, polynomial. We use this term all the time, but sometimes maybe we can forget what it actually means. A polynomial is an expression of terms with variables raised to whole positive numbers. So we're talking about things when I have like x to the power of 3, x squared, x, things like that. This is not when I have radicals. It's not when I have negative exponents. It's not when I have exponential functions, right? Just polynomials. The entire chapter 2 or topic 2 is about polynomials, so that's what we're going to be talking about. The standard form of a polynomial is when the degrees of the terms are in decreasing order. So let's talk about what that means. The degree of the term is determined by the sum of the exponents on the variables. So it's probably been a year since Math 2 when you talked about degree, but what I've got here is I have this example, right? F of x equal to negative 3x to the fourth plus 5x squared minus x minus 13. This first term right here, the degree of this term is degree 4, right? Just determined by the exponent on 4. So when I look at the next term, 5x squared, the exponent on the variable is 2. So this term right here is degree 2. We don't have a visible exponent on the minus x, but we know that if there's no variable there, but I have an x, then that's automatically a 1. So that I would call this a degree 1 term. And on the constant here, minus 13, that has no variable. So we say that that's degree 0. Standard form means that these are written so the degrees of the terms are in decreasing order. If I scramble these in any other direction, it's not in standard form. But because I've got degree 4, degree 2, degree 1, degree 0, and those are in decreasing order, that's standard form. Does that sound all right? So far, so good? Okay. Now, the degree of a polynomial, so here we're talking about degree of each term. The degree of the entire polynomial is determined by the term with the highest degree. So the greatest degree of any term in that polynomial, for example, this whole polynomial is degree 4. So we say that that's a degree 4 polynomial because this term, the largest degree is 4. So whatever the term that has the biggest degree, that's the degree of the whole polynomial. In Math 2, we spend a lot of time talking about polynomials of degree 2, which we also call quadratic, right? So we spend like half the year talking about quadratic functions. In this class, we're going to talk about, I think we talk about like 9 different functions, a whole bunch of them. So, all right, and then this green note down here, the leading coefficient. The leading coefficient is the coefficient of the term with the largest degree. So if it's in standard form, That means the term with the largest degree comes first. The leading coefficient is going to be the number or the coefficient of that variable. So in this case, the leading coefficient is -3. These two parts of a polynomial, the degree of the entire polynomial and the leading coefficient, are the only two things that determine the end behavior of a function. And we'll get into that in a couple minutes. These directions are getting cut off. Let's see if I can fix it. Oh no, I don't want that. Whatever I just did. Don't change my language. That's what I wanted. Okay. So example 1, write each polynomial in standard form, identify the leading coefficient, the degree, and the number of terms. So this is just identifying and rewriting the polynomial. And example A says f of x is equal to 1 plus 2x cubed minus 5x to the fourth plus 6x squared minus 7x to the fifth. So the first goal here is to rewrite this polynomial function. And when I do that, I need to write it in standard form. So for standard form, I'm looking for which term has the highest degree, and then I'm going to write them in that order. So I'm going to slowly break down the first one. I'm going to write the degree on top of each one. So if I have just a number with no variable, that's degree 0. And this step might be unnecessary for you. That's okay. The next term, 2x cubed, the 3 is the exponent on x, so that means that that term is degree 3. Following term minus 5x to the fourth. The 4 on the exponent on the variable determines that that's a degree 4 term. 6x squared, that term is degree 2. Minus 7x to the fifth, that's a degree 5. I need to put these in decreasing order. So when I rewrite, I'm just moving things around. I'm just shifting things around. So no signs are going to change. The degree 5 term is going to go first. So I have negative 7x to the fifth. Then the degree 4 term, minus 5x to the fourth. Degree 3 plus 2x cubed. Degree 2 plus 6x squared. And then I don't have a degree 1, but I do have a degree 0, which is just the constant at the end, plus 1. That's standard form. And then to answer the rest of the prompt, identify the leading coefficient, the degree, and the number of terms. So the leading coefficient, I go to the first term when it's in standard form, and I'm looking for the coefficient, which is going to be this minus 7, negative 7. The degree of the entire polynomial is determined by the term with the highest degree. So that's just going to be a degree 5. And then number of terms, we just count them. Each one of these is a term. So 1, 2, 3, 4, 5 terms. Any questions on those pieces of information or how I wrote it in standard form? Do some of you remember seeing parts of this last year? Talk about it a little bit in math 2. You're like, no, not really. That's okay. Okay, so please write down example B, and I will give you a minute or two to try to answer that question on your own. So put it in standard form. Identify the leading coefficient, the degree, and the number of terms, just like we did for A.
So the leading coefficient will be the one with the biggest exponent?
Yes, it's going to be the coefficient of the term with the biggest exponent. Correct. Yeah. Yes. Cool. All right. So if it's written in correct standard form, I'd have f of x equal to 5x to the 6th plus x to the 4th minus 3x squared minus 10x plus 8. So just double check that you're all good on the answer that you put down on your page. All right. So the leading coefficient and the degree are both going to be determined by whatever the first term is if this is correctly written in standard form. So 5x to the 6th. The leading coefficient then is just 5. It's the coefficient in the lead of the entire polynomial. And the degree is just going to be the highest, so that's degree 6. Count up the number of terms. This has 5 terms again. Just a coincidence. Any questions on those? It's a lot of little concepts kind of packaged together. Okay. So now we're going to move into this idea of end behavior, which will likely be new. The end behavior explains what happens to the graph as x goes to the left and the right. The end behavior is determined by degree of the polynomial and the leading coefficient. And then I'm going to ask that you copy this table into your notes. So I have to zoom out a little bit more. Bless you. So on the table, I've got degree across the top, leading coefficient, a spot for an example, end behavior shape, and end behavior structure. Going down the first column, underneath degree, I have even, even, odd, odd. And underneath leading coefficient, I have positive, negative, positive, negative. You're going to work through an activity that's going to help you fill in these first 2 columns, and then we're going to summarize at the end with that 3rd column. Okay, cool. So the entire Desmos activity was based off of even and odd degree functions and what happens when I have positive and negative leading coefficients. All right. So you could have written infinite number of examples for each one of these. I'm just going to pick the ones that were out of the activity that were towards the end. So any example of an even degree a polynomial with a positive leading coefficient. I'm going to go for 3x to the fourth plus 6x. So my polynomial is an even degree, and my leading coefficient is positive. So if you have something else written down, that's totally cool. You don't have to write mine down. If you want to write mine down in addition, that's cool too. And you were also asked to fill in the next column, the end behavior shape. You could have done this in a couple of different ways. You could have used some little arrows or just maybe sketched a graph. When we're talking about the shape of the graph and looking at end behavior, we're very specifically only looking at what happens at the end. So every time I have an even degree polynomial, both ends either open up or open down. All right, so they either go up and up or down, down. Because it's positive, this is going to be up, up. Now, I don't know what this graph looks like in between. And you'll see it written different ways. So just to show you a variety, you'll see it written where they'll do like some weird dotty stuff in the middle and then finish it like that because they don't care what happens in the middle. What we're talking about here is the end behavior. Oh, those are probably a little hard to see. Let me make them a little bolder. Where I don't really know what happens in the middle. What happens in the middle is determined by everything else that's not to the PR order 4 and not with the 3. And then this last part, this end behavior structure, this is the part that we're going to do together. Because it's a little convoluted, if you will. So we're going to look at the graph. And this last column is not something that we're really focusing on today, just an introduction. We're going to grow with it as we go. But we're going to look at what happens as x goes to the left and what happens as x goes to the right. So this is going to be our structure, and I want to explain it to you. So today, I'm really happy if you can recognize that when this is a 3x to the fourth as my leading term, this goes up and up. Fabulous. Great. That language is wonderful. As we develop and as we mature when talking about end behavior, our structure and our answers are going to look a little bit more like this. Again, today, just introducing it. So what this says is as x goes to negative infinity, this is left, right? X-axis is horizontal. So as I go to the left, what happens vertically? It goes up. Up is just going to be denoted by a positive infinity. As x goes to positive infinity, so as x goes to the right, what happens to y? It also goes up. So this is left, and this is right. It goes up and up. So let's say now I'm looking at a negative coefficient. I'm just going to write down a similar example because it was in your activity. If the leading coefficient is negative instead, if I have a negative 3, how does that change the graph? it's actually going to open down and down. Now, I don't know what this looks like in between. I'm just making something up. It's dashed because who knows what happens in between. It doesn't really matter. I'm really concerned with it, the end behavior going down and down. So hopefully you have something similar drawn. It's okay if it looks different. If you just drew a U opening down, that's fine. But I'm going to do the same thing here. I want to talk about officially, as the graph goes to the left and as the graph goes to the right, what happens to my end behavior. It doesn't have to be a 4th degree polynomial. This could be a 6, this could be an 8, this could be a 2. As long as the largest one is even and it has a negative coefficient, then it's going to go down, down. So as x goes to negative infinity, so as I look to the graph to the left, what happens vertically? It goes down. So down will be represented by negative infinity because we're talking about y. As x goes to infinity, so for the x-axis, infinity is positive, so I'm going to go to the right. What happens to the y? What happens vertically? It goes down. All right, you got a few more slides in, and then you started talking about, okay, well, now let's look at if I have what's called an odd function, odd polynomial function. And the example that was towards the end of your slides was 3x to the 5th plus 6x. And they showed you a whole bunch of different functions with odd highest degrees. And they all had something in common. They all went up to the right, and then something might happen in the middle, and then they went down to the left. So remember, these are just examples. It doesn't matter if my leading coefficient here is any odd number, 5, 7, 9, 3, 1. If my leading coefficient is positive, it's going to go up to the right and down to the left. So as I look to the graph to the left, right, x goes to negative infinity just means as I look left, this goes down. Y goes to negative infinity. So it goes down to the left. And as I look to the graph to the right, as x goes to positive infinity, as I go to big numbers on x, this goes up. Up is positive infinity. So something like 3x to the fifth goes down to the left and up to the right. All right, and then if I have a negative coefficient and an odd exponent, this will go up to the left. And I don't know what happens in the middle. It's not really my focus. But it'll go down to the right. Structure starts off the same. As x goes to the left, y goes up. And as y goes to the right, as x goes to the right, y goes down. Points of the function. What I'm going to do is I'm going to go over to Desmos. I'm going to graph these. I'm going to come back and sketch the important parts. So we want to know the intercepts and we want to know roughly where they're changing directions. So when I graph these, I'm going to look for where the x-intercepts and the y-intercepts and the general shape of things. So I'm going to, hopefully you have this written down because I'm going to go ahead and type this into my Desmos. You can type y equals or f of x equals. Remember, to get your exponent, you're going to type shift 6. And then you can scroll to the right to get out of the exponent position. So in my current view, I can't really see a whole lot of what's going on. Yeah, just the intercept, not the coordinate. Yeah. I'm going to zoom out so I can get an idea of what this graph looks like more thoroughly. So when I zoom out, I get this. I get this W shape, but I want to know where my intercepts are. When I zoom in down here, I've got a y-intercept at negative 27. And x-intercepts, it looks like 3 and negative 3. Now I can use my pointer and click on here, and it'll tell me where those points are, which is kind of nice. So I just clicked where the intercepts are. So I can see them really clearly, right? Love Desmos. So I'm going to go back to my notebook and I'm going to sketch this. It's not going to be to scale. It's going to be more of a sketch, and I'm just going to hit the intercepts and get the general shape of things. So the general shape is kind of this W shape. And my graph showed it crossed at 3 and -3. And my y-intercept was down here at -27. So a real loose sketch. Okay. I checked your Savas homework that goes with 2-1, and it doesn't want coordinates. It just wants you to list the intercepts. So in this case, my intercepts are going to be -3, 3. That's where they cross the x-axis. And then my y-intercept, it crosses at -27. Just like when I talked about intervals before, when I'm talking about between what numbers or at a number, I'm always going to be talking about the x values, and that's going to be no different from when I'm talking about the turning point. So I've got some places here. They're not asking you to find the relative maximum or minimum. Okay, I don't need to find where this is. It's just saying between what x values does that occur? So I don't know. It occurs somewhere between here and here, between 0 and -3 or -3 and 0. There's another turning point right here, which occurs at 0. And then there's another turning point here, between here, 0 and 3. So you're just kind of estimating. It's not looking for you to pick up a decimal or anything. It's just saying at or between what numbers. So the turning points occur between -3 and 0. Right? Here's a turning point here. One occurs at 0. And then the last one occurs over here somewhere, which, remember, I'm just talking about x values. So that occurs somewhere between 0 and 3. We're just sticking with some vagueness there. So read that over and see if you have a question. Question on intercepts or estimating where turning points are? Okay. Here's a second example. F of x equals x to the third minus 13x plus 12. So we're going to do the same thing, graph it in Desmos, come back over here, sketch it, pick out the important pieces for the x and y intercepts, and about where those turning points are landing. So I'm going to head back to Desmos and graph a new function. Now I have x to the power of 3. Scroll right to get out of the exponent. Minus 13x plus 12. Desmos is so nice. It puts these little gray dots right at my intercepts. If I click them, it'll actually show me the coordinate. But I want to see more of what this graph looks like, so I'm going to zoom out. This gives me a general shape. It looks like it goes up to about 30, down to about -5. I'm curious to see where this crosses the y-axis, so I'm going to zoom back in. It looks like a -12 to me. So kind of gathering this information, I'm going to come and take it back to the other screen. So it crosses the y-axis at 12 and the x-axis at -4, 1, and 3. So my x-intercepts are just those values where the graph crosses the x-axis. Again, Savas is asking that you write them as a list instead of as coordinates this time. And the y-intercept where the graph crossed the y-axis, which was at 12. This time I only have 2 turning points. So I've got one here, which occurs between these 2 intercepts, and I have one here that occurs between these 2 intercepts. Right? In between here and here, and in between here and here. So this first one, the turning point, occurs between -4 and 1. And the other one occurs between 1 and 3. Just a general idea of where that happens.